For this part of the chapter on geologic time, I'll be going into more detail about the principles of relative dating. If you remember, these were set forth by Charles Lyell in his textbook Principles of Geology, and they are the principle of superposition, which says that in a sequence of undeformed sedimentary rocks, the relative ages are determined by the sequence, with the oldest rocks being on the bottom and the youngest at the top. The principle of original horizontality tells us that sediments are deposited in a horizontal or nearly horizontal layers. Principle of lateral continuity says that rocks are continuous with the depositional environment. Remember depositional environments from the sedimentary rock chapter. Sedimentary depositional environments can include a number of things, like a beach, like the bottom of the ocean floor, like a floodplain, like a delta, alluvial fan, and on and on and on. And those have continuity. Then the principle of cross-cutting relationships or intrusions, the principle of baked contacts, and the principle of inclusions. Remember these because they are important for relative dating of geologic events. Before the discovery of radioactive isotopes, these were the only methods that geologists had at their disposal to try to figure out the sequence of events on Earth. Remember, the rocks are recording the history of what was going on at the time. And I'll add another one in here. And I'm not sure that Lyell knew about these. Maybe he did, but it's unconformities. There are several different types, and we'll talk about those different types. So this is principle of superposition and the principle of original horizontality. And you can see that we have the oldest rocks on the bottom here, and then the youngest rocks would be on top. That's just common sense. Think about wallpaper on a wall. That's a house that's 50 years old, and there have been all sorts of different layers of wallpaper. The oldest one will be on the bottom. The most recent one will be at the top. And then this is the principle of original horizontality. When sediments are first deposited, they are horizontal or nearly horizontal. So how do we use this? We know if we see rocks that are folded or faulted in the field, that whatever happened to those rocks happened after they were originally deposited. Then the principle of lateral continuity says that rock layers will extend laterally until they thin out to nothing. Well, again, this makes sense because depositional environments aren't going to extend to infinity. At some point, a beach will run out. At some point, there will be no more floodplain. So the rocks then will extend. The rocks that form from those sediments will have continuity over whatever continuity that depositional environment had. And even though some of them might be missing, as you see right here, these were ocean floor rocks that are now exposed to the surface, and a river has downcut through the rock layers. So the rocks are going to be missing in here, but they are found from one side of the canyon to the other. So these rocks are said to have lateral continuity. All of these have lateral continuity. And this is lateral continuity illustrated. This is sandstone. You see formations like these in Utah and Arizona and Nevada. They have lateral continuity. This was all one big depositional environment at the time. So a lot of sand dunes here, desert sand dunes that had continuity. So even though the rocks are missing, we can correlate the rocks to these other sections. And then this is an O. Let me see if you know. Did you say it? This is a geologic structure called an anticline. This is a fold. So we have, once these rocks were exposed at the surface, we have some of them that have eroded away, but if we were doing geologic mapping in the field, then we would see that these rocks are going to match up with these, and these rocks will match up with these, and these with these, and so on and so forth. So lateral continuity. Then we have three principles illustrated here. These are the principles of original horizontality. When these rocks were deposited, they were horizontal. Superposition, the older rocks will be at the bottom, the younger rocks will be at the top. And lateral continuity. And we can see that from just looking at these different color layers, and you see what an extent they have, how continuous they are throughout this area. This is Bryce Canyon. Bryce Canyon is a national park in Utah. There are lots of beautiful national parks in Utah. So again, principles of relative dating. And then the Grand Canyon makes a great illustration of lateral continuity too. These rocks, just pick any layer and you can track them over very long areas, not just in what you see in this picture either. They have even more of an extent than that. This is the Kaibab limestone up here, so we know there was an ocean at one time. As we cross the canyon, we see, oh, it's missing, but on the other side of the canyon, we can pick it up once more. Lateral continuity. Then cross-cutting relationships or intrusions. We see that these rocks here are folded, so we know that they had to be at depth when that happened. They had to be ductile. And what we see are these intrusions. These are magmatic intrusions or igneous intrusions, so it's where magma found room for itself in these rocks. Maybe a weak area, maybe a fracture, and the magma very rudely penetrated into these rocks. So we know that the rocks had to be here before the magma could intrude on the rocks. So these rocks out here are older and the intrusions are younger. So intrusions are younger than the rocks that they intrude into. Faulting would be the same way. If we find rocks that are faulted, we know that the rocks had to be there before they could be faulted. So the fault is younger than the rocks. Cross-cutting relationships or intrusions. Here's another one. And look at this. This is a huge road cut. This is a person right here. This is a road that they're walking down. So we know that those rocks were horizontal or nearly horizontal when the sediments were deposited, and then the rocks that formed from those sediments were horizontal or nearly horizontal. So we know that they have been acted upon by another force, a tectonic force. And in this case, it's compression. So this looks like it's going into an anticline over here. And then this would be the limbs of the anticline, and it would be the limbs of an adjacent syncline, which would be over here. So folded. Again, this had to happen at depth. Inclusions, principle of inclusions. Inclusions are going to be inclusions that are found in rocks are older than the rocks that they are found in. So we have a couple of examples here. Here's a good example, a real world example. If you've traveled into the Sierra Nevada, you've probably seen in that speckled grano diorite that the Sierra Nevada mountains are composed of, you probably have seen these big dark color splotches in the rock. Well, those are inclusions. These inclusions are referred to or called xenoliths. Xeno means foreign, lith means rock. so foreign rock. These are called foreign rocks, but that's kind of a misnomer because these were not the foreign rocks. They were pre-existing. These were rocks that were there at the time. And then the batholith formed, magma chamber formed, and as that magma chamber rose up under the rocks, it plucked off pieces of the rocks that fell into the magma chamber, and the magma wasn't hot enough to melt those rocks. So when the magma solidified, these inclusions ended up being included in the rock itself. So those rocks are older. Inclusions are older than the rocks that they are contained in. All right, so unconformities. This was not one of Lyell, as far as I know, this is not one of Lyell's principle of relative dating, but they are good for that. So there are three kinds of unconformities, and an unconformity is a gap in the rock record, and that means that one of two things took place. Either the rocks were never there to begin with, or they were there and they were eroded away. And it's a pretty good bet that they were there and they ended up being eroded or destroyed in some manner. So there are three types of them. There are disconformities, there are angular unconformities, and there are nonconformities. So let's just pick the disconformity first. In textbooks and in lab manuals, the disconformity or the unconformity is shown with a wiggly line. So what we're seeing here is we have sedimentary rocks above and below, or flat-lying rocks above and below, and those are usually sedimentary rocks. There are exceptions to that, but usually sedimentary rocks. And if we were just in the field, all we would see is just layer after layer after layer of rock. We're not going to see a wiggly line in the rocks in the field. But in geologic mapping, we know that they are there, and we know that they represent missing time. So we might have rocks of Cambrian age down here, and we might have rocks of Jurassic age up here. So we would have to look for fossils or some other indicators that maybe we've got this huge chunk of time that's missing here. Then an angular unconformity, those are the ones that are pretty easy to, oh, let me find an empty spot down here, that are pretty easy to recognize because we have the let me find my pencil where you're going to go here. You have the unconformity surface, and the rocks below it are tilted or folded. And then you have the rocks above. So that's an angular unconformity. That is the type of unconformity that James Hutton saw on Sycamore Point on the coast of Scotland, and he realized that the Earth is way older than 6,000 years old. Otherwise, those rocks couldn't be that way. Then a nonconformity is like this. Nonconformity, we have our wiggly line, and then below that line there are going to be crystalline rocks, and that code is usually something like this, little X's or little V's that indicate crystalline rocks. Okay, well, what rocks are crystalline? It's usually going to be an igneous rock. That could be granite or granodiorite, an igneous rock, or a metamorphic rock. So it's igneous or metamorphic below the unconformity surface. That's a nonconformity. So a disconformity, an angular unconformity, and a nonconformity. Missing time from here to here. Missing time from here to here. Missing time from here to here. One way that we would know, let's say our fossils in these rocks down here were blue-green algae, something very simple, and then we go up here and we have, fish fossils or something. So we know that we have a chunk of missing time here. And this is Sycamore Point. This is the unconformity surface right here. between the rocks that are tilted below and these rocks that are on top. See that a little better right here. So these rocks are gray-wacky, Silurian in age, 435 million years old. And sitting on top of this erosion surface are these Devonian sandstones, which are about 370 million years old. So between the top part of the gray-wacky and the bottom part of the sandstone, there's 65 million years of geologic history that we don't have. We don't know what was going on, but we can bet that there was something going on. 65 million years worth of something. All right, so this is some stepped art here that will show you all three different types of unconformities. We start out here with what looks to be metamorphic or igneous rocks down here, and we have an ocean that has transgressed, and we have sediments that are being deposited on top of those rocks. So what do we have going on here? We have a nonconformity. Let's keep going here. The ocean recedes, sea level drops, and then those rocks that were forming are exposed at the surface. And we have something else that has gone on here. They have been tilted. Okay? So new rocks exposed at the surface when the ocean recedes. Let's bring the ocean back. The ocean comes back, more sediments are being deposited that will turn into rocks on top of those tilted rocks. So you know what we have here. Say it with me. We have an angular unconformity. Rocks are tilted underneath. All right. So after that, ocean recedes once more and a new surface is exposed. We have some tectonic uplift going on, some distortion of the rock strata. Ocean comes back in, and on top of those flatline rocks below, we have more sediments that are being deposited, and between the two, we have a disconformity. So a nonconformity, an angular unconformity. Whoops, I know you all tired of me saying this, but angular unconformity and disconformity. And that's just the cycle of rocks on Earth. Ocean level rising, ocean level falling. Okay, so this is Grand Canyon. This is the Vishnu schist in the Grand Canyon. It's about 1,700 million years old, or 1.7 billion years old. And deposited right on top of this is the Tapete sandstone, which is 550 million years old. Okay, what do we got going on here? We have a lot of time that's missing between where these red lines are here, the Vishnu schist and the Tapetes above. We have about 1.5 billion years missing. Now we know, we have to know that there were things that were going on. Earth is dynamic. It's not going to just halt for 1.5 billion years. But what happened to those rocks? We don't have a rock record from that time. So it's a mystery what happened, but you can bet there was a lot that had happened. That's called the Great Unconformity. And let's just say that this rock here is granite. It's all stained, so it's hard to see what it is, but for our purposes here, we're going to call it granite. And you might be saying to yourself, well, okay, what about the fact that these rocks are tilted on top? Remember, here's our unconformity surface. So the rocks on top of that are tilted. Well, that doesn't matter. We're looking at the rocks underneath. And if it's a granite, which is a crystalline rock, then this is going to be a non-conformity. Okay? Then we can add fossils to the picture. I've saved the best for last here. The fossils get added to the picture of relative dating through the principle of fossil succession. And this idea was developed by William Smith, nicknamed Strata Smith, who later on became known as the father of English geology. He was not a geologist. He was a canal builder. He built canals all over Great Britain, and he started noticing that the rocks that he was excavating were arranged in layers. Not a big whoop. Everybody had seen layered rocks, but because of what he was seeing in these rocks, fossils, he was able to understand that fossils found in one layer were very different from fossils found in another layer. Where he found one type of fossil in these rock layers, he didn't find those fossils above or below those rock layers. So if he found those fossils in a rock layer far away, he could correlate those to the same event, the same time frame on Earth. And that was a huge step in the development of the science of geology. Geology was really coming into its own as a science with the contributions of William Smith. Before, geology was known as natural history, but it really came into its own when William Smith had his aha moment by being able to follow these rock layers because of the fossils that were contained within them. So he ended up being cheated out of all this data that he had. He had reams and reams of fossil diagrams of diagrams of these rock layers. And he came up with what is called the first geologic map of its kind. But he didn't end up getting credit for it until he was a much older man. And at long last, he did become the leading light that he should have been early on. And the king ended up giving him an allowance for the rest of his life, which wasn't longer after that point. And this is the map that he drew. These show the coal measures across Great Britain and the codes that he used to indicate the same type of rocks. So there is a book by Simon Winchester, one of my favorite authors, called The Map That Changed the World, and it really did. Anywhere these rocks were found, not just in Great Britain, but anywhere in the world, now people realized that if those fossils were found in those rocks could be correlated to the same time period. And that was fantastic. There he is. Yeah, at one point in his life, he ended up going into debtor's prison. And we're looking at correlations here. So we can do that from place to place to place. We can do that based on the similarity of the rock, but we can also do it based on the presence of fossils. Index fossils are the best because they are species that live for a short time, but they had a geographic, they were distributed geographically over very large areas. So anytime you find a rock, no matter where it is in the world, anytime you find a rock with those particular species in it, we can correlate those rocks from place to place, and we know that they are of the same time period. Okay, so I'm going to stop there. Next time I will pick up with numerical dating, radioactive isotopes, and talk to you about how half-life works. All right, see you later.